So now that you've refreshed your memory on what IMFAs are, let's talk about some of the properties that those IMFAs can lead to. So it's going to help control melting points and boiling points. So if you have a stronger IMFA, it's obviously going to take more energy to break those IMFAs apart. And if you have a bigger molar mass, it's going to take more energy to break those IMFAs apart for two reasons. Number one, bigger molar mass probably implies that you either have bigger molecules, so more IMFAs, or you have bigger atoms, which means that you can polarize the atom a little bit better. So as the electrons are moving, you can get the electrons to shift one side or the other and have a bigger shift with those electrons, so a bigger temporary dipole can be created. Other consequences in terms of mixing, what substances will dissolve in what substances. Similar IMFAs are going to interact with each other easily. Different IMFAs will not. And so the idea that we learned in first year was like dissolves like. So two polar things will very easily interact. A polar and an ionic thing will very easily interact. But something that is nonpolar, like oil, doesn't mix with something that is polar, like water. And for metallic stuff, obviously, as long as you can have delocalized electrons, you're going to have interactions. So this continues the idea nonpolar things mix well with nonpolar things, polar things mix well with polar things, but you get them separate, and it's not going to work. Other physical properties that are controlled by IMFAs that we will get into taking a look at: strength, conductivity, and so forth. So in terms of predicting melting points and boiling points, like we said before, the stronger IMFAs are going to cause higher melting and boiling points. And why is this? When atoms or ions or molecules are more strongly attracted to each other, the temperature is going to have to go higher in order to overcome those attractions. More polar molecules are going to have higher melting points and boiling points because their attractions are going to be stronger. Atoms and molecules that are heavier or larger, like we said before, are generally going to have higher melting points and boiling points, again, because you can get either more IMFAs or you can polarize the molecules a little bit better. So there's all those ideas. So in terms of being able to predict melting points and boiling points, for van der Waals IMFA, so that's for molecular substances. So what are you going to need to do? You're going to have to sort the substances into what categories they are. Then you're going to have to sort each of those categories from lightest to heaviest. So in terms of molar masses. For metals, one additional other additional factors are going to have to be considered. We're not going to worry about metallic things. For ionic things, we've got Coulomb's law to consider. Charge and size influences are going to help with the melting points and boiling points of ionic things. So sticking with this idea of boiling points and melting points, if you sort the IMFAs by their molar mass, so for example, if we do the halogens, all of them are nonpolar, so they're all going to form London forces. From lowest to highest melting point matches lightest to heaviest. Fluorine, which is the smallest, has the lowest melting point. Chlorine follows, bromine, and iodine. And again, the reason for that is because fluorine is so small that we can't polarize that molecule very well. But iodine, being much larger, has many more electrons. We're going to be able to get those electrons shifting much more easily. Boiling point, you see the same way. Notice that for bromine and iodine, their boiling points are actually above room temp, which is why they're a liquid and solids at room temperature. So, like we said, these two guys are going to be gases. Bromine's going to be a liquid. Iodine's going to be a solid at room temp. Because iodine is a larger atom, you can polarize it better. If we do the same idea, but looking at similar molar masses, but different IMFAs, so we're going to look at some organic molecules. All of them are about 60 grams per mole, but they have different types of IMFAs. So, for example, butane is nonpolar because it's got just C's and H's. If we go to methyl ethyl ether, which is very similar in molar mass, but the ether means we have an oxygen in the chain, so we've broken up this chain a little bit and stuck an oxygen in there. So we have a slight area of polarity here. We go to acetone, which is even more polar, so rather than the oxygen being in the chain, we have a double bonded oxygen. So that makes this molecule more polar. And then finally we have something like propanol, which has a hydrogen bonding area potential. So we're going to have much stronger IMFAs being formed here. Now, you still have London forces being formed here, but the fact that you've got an OH here that can hydrogen bond, it makes it much stronger. And then finally you get to something like ethylene glycol, which has 2 OHs as opposed to 1 OH, even stronger. So if you look at those temperatures, ethylene glycol, definitely a liquid at room temp. Propanol's a liquid. Acetone's a liquid at room temp. These guys, gases at room temp. So the stronger the IMFA, the higher the boiling point it's going to be. All right, so now let's take a look at the concept of isomers. So remember that we're looking at same structural formula, same molecular formula, but different structural formulas. So this is a little hard to see. You have normal pentane with spit it out, which is just 5 carbons in a row, versus neopentane. So you have 1 central carbon and you have 4 methyl groups coming around the outside. Or I compare glycerol with 1 propanol, so I've got more OHs. Why are these isomers? More OHs than I do in propanol. Or I have propanol, these are definitely isomers, versus methyl ethyl ketone. Or I have butane versus 2-methylbutane. So again, like over here with the pentane, we've got 4 carbons in a chain. Here we have 1 carbon as a branch. And then finally we've got 1 propanol, which is the OH on the end, versus 2 propanol, which is the OH in the center. So what's going to happen in terms of boiling points and melting points? Well, as you add chains or branches like these guys to carbons, you are going to see that the melting point actually goes down. Notice that the temperature drops because that branch is not allowing the atoms of the molecule to interact as well. If you have a straight chain, you have a long flat surface area for the most part where you can have interactions. Once you start putting branches on there, now you have spikes sticking off, the chances of more attractions is going to go down. So the same idea here. They both weigh the same, but the fact that you have a branch is going to mean that this boiling point or melting point is going to be smaller. Okay, how about something like this? Well, we've already seen glycerol has a much higher melting point than propanol does because the 3 OHs is much stronger than just the 1 OH. If we take a look at propanol versus methyl ethyl ether, again, we've got the ability to form a dipole interaction, but here we have the ability to form a hydrogen bond. So you see that propanol is a much higher temperature than ethyl methyl ether. And what do you think about here? What's going to happen between regular propanol, 1 propanol and 2 propanol? You're going to have the 1-propanol be slightly higher because you have that straight chain, whereas the OH is sticking out, so you have a strong bond there, but the rest of the molecule can't form London forces, whereas here you can form London forces and an OH. So this is going to have a slightly higher melting point than the isopropyl alcohol will. All right, so let's take a look at summarizing some of these properties. So in terms of strength, we already learned it increases as you go from weakest to strongest. These guys are going to be soft and brittle, if they even are solids at room temp. Here you've got something that's relatively strong, malleable and ductile, because as long as we can have those overlapping orbitals overlap with some atoms, the atoms are very willing to shift what orbitals they overlap with. So you're easily able to manipulate them, but they are very strong but manipulative. Ionic compounds, hard but brittle. We saw that in the one demo slide in the previous video. And then network, very, very hard. Melting points and boiling points, from low to high, depending upon strength. Conductivity, that's one thing we haven't talked about. The ability of charged particles to flow through it. Well, molecular substances don't have charged particles, so they're not going to be able to conduct. Metallic substances have flowing ion or electrons, so of course they're going to be able to conduct. They've got those delocalized electrons. Ionic substances will conduct only if they're melted or dissolved, because you can have the ions moving. If you have a solid, however, ionic substances aren't going to conduct. And then networks won't conduct except for, graphite, because of the organization of that one orbital is empty, so you can have conductivity there. Last idea, I'm running out of time, so I'm talking a little faster here. Soaps and emulsifiers. So a soap looks something like this. It has a polar end that will interact with water, but then it has a very long nonpolar end that will interact with all the dirt and the grease and the grime on you. So you put soap on your body, this attaches to the dirt, and as you stand under the shower, the water gets attracted to the water, the polar end here, and all of it gets washed away. So here's an example of where you have molecules that aren't just polar or nonpolar, but they have ends, and that actually comes into play a lot when we start taking a look at bigger molecules and more realistic molecules. So like I said, you got the nonpolar end, you got the polar end. The dirt is going to interact with that nonpolar end. The water interacts with the polar end and washes the dirt away. So all right, so last idea. You remember the micelles from bio, or the lipid bilayer of the cell membrane. Soaps and emulsifiers kind of do that same thing. You get the soap molecule to surround the oil droplet or interact with the oil droplet, and then the polar part of the water surrounds around the outside. So they call the, you probably remember this from bio, well maybe not, bio, it's been a while. This is the hydrophobic end, it's afraid of water, that's the nonpolar part, and that's the hydrophilic end, that's what will interact with water. So you can see molecules can be much more complicated than just straight up polar or nonpolar. And I think that takes us to the last one, which is good because we almost are time up. All right, so next version, our next conversation is going to be about the properties of strictly liquids.